Hi everyone. In this video I'm going to teach you how to calculate cell voltage for these galvanic slash voltaic cells. Remember, galvanic and voltaic are synonyms for each other. This is when our delta G is going to be negative. Spontaneous cells, electrons are going to spontaneously flow from one cell of our battery to another one. This looks a lot like the single replacement reactions you did in pre-EP, so a lot of these reactions, once we get them going, you'll see some familiarity there. So to do this, it's really pretty simple. At the bottom of the screen, you'll see in red the quote-unquote equation that we're going to use. Really all we're looking at is a difference between the two potential cells. Remember, we've got two cells in our battery. Which one wants to gain the electrons more than the other ones? The one that wants to gain the electrons more, call it electronegativity, is going to sort of draw the electrons toward it. And that's going to be the cathode. That's where the reduction is going to take place. So all we're going to do is take the cathode reduction potential and subtract from that the anode reduction potential. So I was using the phrase there, reduction potential. What is that? Well, what we're doing is we're taking the potential half reactions for the two cells. And I'll do an example here and you'll see what I'm talking about. But let's pretend like we had zinc and copper. So if we have zinc and copper, I have zinc plus 2 that has the potential to be reduced to zinc metal, and I have copper 2, which also has the potential to be reduced to copper metal. And so what I do is look at the voltage, in other words, the likelihood of those two metals, those two ions being reduced to their metals. And I write it in terms of the reduction, and we're just comparing the reduction. Now, there's no great reason for us to do that. It was just decided many, many years ago that that's kind of what people wanted to look at, reduction potentials. They could have done oxidation, but they chose to do reduction potentials. Now, where did the numbers come from? Well, again, it was decided when this was first getting started. If you look in the middle of the screen on the PowerPoint, they decided to use hydrogen reduction as the standard. And so they look at the equation here. Hydrogen ion gains electrons and reduces to diatomic hydrogen. And they said, let's make this voltage be 0. So everything else we see is just in comparison to hydrogen's ability to gain an electron. If it's more positive, that means you have something that really wants to gain an electron more than hydrogen. And if it's negative, something that when you compare it to the hydrogen doesn't really want to gain an electron. So if you look at the next slide, here is a table of reduction potentials. And so what you always have to do is find the exact reduction that you're looking for. Just a couple of highlights on here. You see up here where voltage is 0. This is the hydrogen. This is the standard. And then at the top on the left, you see that fluoride is the most positive voltage, which means it is the most easily reduced, and that probably makes sense to you. On the other end of the spectrum, you see that the lithium cation really doesn't want to be reduced, so it has a negative voltage. It doesn't want to happen. You see a lot of crazy, some very simple things here. Lead 2 reduced to lead, that's pretty simple. Some intermediate stuff like chromium 3 being reduced to chromium 2, kind of strange. And some more difficult stuff like the dichromate reduction reaction over here being reduced to chromium 3. That may look more familiar if you've done your balancing half reactions. So when we have a potential reaction, we have to go to these reduction tables, pick the half reactions that are going to be useful to us, and bring it out and do the subtraction. So let's do an example. In this first example, we have cadmium and tin. So if I'm making my voltaic cell, I'm going to have a piece of metal, cadmium metal, and I'll have a piece of tin metal on each of my electrodes in a solution of maybe cadmium 2 nitrate, tin 2 nitrate. Now I'm going to go to my table. I'm going to find those two half reactions. And you can see here that both of these have negative voltages. So right away you may think this reaction isn't going to happen. Remember, this is just in comparison to hydrogen. These don't want to gain electrons as much as hydrogen does. But that don't mean there's not a difference between them. Electrons here will still flow to the element, or sorry, to the ion that wants to gain electrons the most. In this case, we always look for the most positive. No matter if it's two negative numbers, two positive numbers, one positive, one negative, the more positive of the two numbers is going to be your cathode reaction. So for this example, it will be the 10-2 reduction. That's going to be your cathode. So once you get that, we're just going to take cathode minus anode. We're not going to swap signs. We're not going to swap reactions. I'm simply going to take the two numbers in red and subtract cathode minus the anode. So the math ends up being pretty simple. And we calculate a cell potential here, standard cell potential of 0.267 volts. So that means this is a spontaneous cell. We have a positive voltage. All right, so now we're going to flip over and look at the example sheet. We'll do a few of these. I probably won't do the whole thing for you. It's going to be a little tricky doing it in this format, but we'll make it. So in number 1, I'll tell you what I'm going to do is to save time, I'm going to be using the PowerPoint, and I'm going to pull the numbers off myself so you guys don't have to watch me go back and forth. So I've got that done. All right, so let's start with number 1. So calculate the standard cell potential produced by a galvanic cell consisting of a nickel electrode in contact with nickel 2 ions. So that's one electrode. And basically what that's telling us is that we're going to have nickel plus 2 plus 2 electrons. And that's going to make nickel solid. And then the other reaction that we're working with here is silver. So silver ions, and they will add just 1 electron. And that'll make silver metal. So those are the two potential reactions we have to be the cathode. To figure out which one's gonna work, I go to my reduction table, and again, I've done this for you. So the reduction potential for the nickel is negative 0.23 volts. And for the silver, it's positive 0.8 volts. So when we look at it like this, we definitely, that's the wrong thing to do. We definitely have the cathode reaction here being the silver. So now to find my cell potential, all I'm going to do is subtract the 0.8 minus, don't lose that negative sign. That's very important. Negative 0.23 volts. And that'll give me, if I did my math correctly, 1.03 volts. So that will be the voltage for this first cell. All right, let's do maybe just 1 or 2 more. All right, so number 2 here, we got what is the voltage produced by a galvanic cell consisting of an aluminum electrode in contact with aluminum and an iron electrode in contact with iron 2, which is the anode, which is the cathode. All right, so kind of the same thing here. I've got aluminum, and aluminum to be reduced will need 3 electrons to make aluminum metal, and iron 2 would need 2 electrons to make iron metal. All right, so I go to my standard reduction. Everything I know about aluminum 3 tells me it does not want to be reduced. It likes being plus 3. So I do go to my table and see a negative 1.66 volts. That is not surprising at all for aluminum. Probably not going to see a heck of a lot of desire on iron's part either. Iron loves to be plus 2. In fact, we get negative 0.44 volts. So once again, we have 2 negative numbers. The most positive of the 2 will be my cathode. And so to figure out the voltage for this one, E cell is going to equal that negative 0.44 minus negative 1.66. So this cell will have a voltage positive 1.22 volts. So once again, we have another spontaneous cell. So that's all you have to do. It's pretty straightforward. Now, historically, what I've seen with students is they get confused. Well, not really confusion maybe, but you get locked in on a how to do it. And I've kind of told you guys about this in the past, that you memorize steps. Well, there's kind of two different ways to approach a galvanic cell problem. The first type is the ones that we've been working right here, where I just give you two electrodes and say, figure out which way the electrons are going to flow. Because electrons will always flow one direction, okay? It's a unidirectional spontaneous thing. They're going to go to the electrode that has the lowest or the most positive reduction potential, okay? So that's when you just throw them together and see what happens. The type of problem that catches students the most, if you look at the screen, is on page 3 of this handout. And you can see the difference in these type of problems. In this problem here, number 11, you don't get the luxury of throwing two electrodes together and saying, which way are they going to flow? When you're given an equation like this, you're being told what directions you want the electrons to try to flow. And the voltages in these problems, when you're given a reaction like this, can be positive or negative. You want to see if this reaction is spontaneous or not as written. So we don't get the choice of picking the most positive. So this is the second type. So for this reaction, I want you to kind of look here with me at what's happening. I can see my calcium here in 11A is plus 2, and on the product side it goes to 0. So what I'm dealing with here is calcium 2 plus 2 electrons is being reduced to calcium metal. Already, I don't have to do anything. That is a reduction, so this is my cathode. And that's just all there is to it. It is the cathode. Whereas now the iodide, 2I negative, is going to go to I2. So iodine is going from -1 to diatomic iodine, so it has to release 2 electrons. So as that's written, that is without a doubt the anode. So you don't have to worry about figuring out which is which when you're given the equation. But I still need to go to my chart and I need to find this cathode half reaction. So I have it written down here. So for calcium, it's negative 2.76 volts. That is the reduction potential for calcium. Now I'm going to come down here to the anode, and even though it is the anode reaction, I am still going to use the reduction potential from the chart for iodide. It's going to look different. You're not going to see 2I minus goes to I2. You're going to see on the chart I2 plus 2 electrons goes to 2I minus. That's just the way they're written in terms of reduction. But when you find it, you'll see that it's positive 0.54 volts. Now again, we're told what's happening here. We don't get a choice. Even though the iodide is most positive, it is not the cathode. The reaction tells us calcium is the cathode. So to find this cell potential, I'm going to take cathode minus anode, and that is it. Negative 2.76 minus 0.54. And that's going to give me, a negative number, negative 3.30 volts. So this reaction here is non-spontaneous. It actually will not be a galvanic cell. It is non-spontaneous as written. And that's just the way it works out. All right, I was trying to think here if we needed to work maybe part B here. I don't think so. I think that's enough to get you going here. So what I want you to do is to work on the practice here, and I'll post the key. If you have any questions, you can find me and we'll work them out either on Zoom or you can email me, whatever you need to do.